Welcome everybody to our live event in March. Today we're going to talk about the quality of cryopreservation. For many times, in the past we had questions about quality of cryopreservation. Of course, we talked a lot about quality of cryopreservation. So we wanted to do a dedicated live event where I'll introduce probably some of those things I will have already said in the past, or reintroduce how we think about quality, what are the metrics that we use, what are our guiding principles to quality, and so on and so on. And of course, with every webinar or live event, we have a Q&A section at the end. So you're more than welcome to ask any question that you might have. And I'll show you the link in a bit. For those of you who have not been around that much or have maybe not joined many of our events, and this might even be the very first event, let me briefly introduce myself and us. I'm Emil. I'm the founder and CEO of Tomorrow.bio. Tomorrow.bio is an organization that does cryopreservations, of course, here, as you might know, in Europe and in the US. I need access to the slides real quick, and then I can also show you the next slide. You need to click into the slides once. Perfect. Now here we go. So we're a cryopreservation organization, as I said, based in Europe, covering the US, with a variety of medical teams. Some of you, of course, have seen them in person with these ambulances, right? Ambulances that we buy and then retrofit to be pretty much mobile operating rooms, so that the whole procedure for perfusion, so the field cryoprotection, can be done in these ambulances. This is one of our ambulances here, the one based in Switzerland, but we also have them in Berlin, we have them in Europe, like in multiple locations, and then last but not least, of course, also in 3 locations now in the US. Cryopreservation, of course, is one part, or the cryoprotection is one part, and then the long-term storage is the other part. This is here at our facility in Switzerland, cryopreservation storage here underground. This is one of our doors. This is the facility from the outside. Some of you, again, might have seen it already in person. For those of you who have not seen it yet, at least about once a year, maybe twice a year, we organize open houses. So you're more than welcome to visit us there in Switzerland and see for yourself. By now, to kind of conclude the introduction, by looking at CT scans, we're by far the organization with the best cryopreservation quality. We have the most field cryoprotection teams in Europe and in the US. Most other organizations actually don't even do field cryoprotection. And last but not least, we're by far the fastest growing organization. You might see this kind of small chart there. This is the first 5 or 6 years of organizations that started, of course, many years before us, and then us. The blue line is us. The green line is all other organizations together. So there's a good amount of difference. Of course, this is not a 100% fair comparison, because, of course, in the past there were different times than there are today. Of course, today, now this topic might be significantly more well known. Nevertheless, even if you compare our current growth to last year's growth of other organizations, then we're still significantly faster and growing. But, of course, none of that is the topic of today. Today, we would talk about quality of cryopreservation. This is the QR code. Either scan the QR code or go to this web page that you see here. There you can ask questions and you can upvote questions. So if someone else has asked a question that you feel like is super, super meaningful, then feel free to upvote it, and then in the end, we're going to go by priority. Today, we're going to focus again on questions about quality, right? All the other questions we're going to maybe very quickly answer, or maybe postpone those questions for next time. I'm going to announce in another event at the end of this one. The next one is going to be a Q&A session, an AMA, with Fernando and me, the founders of Tomorrow.bio, and there you can ask any questions from the broadest set of topics that you might be interested in. Today, we're going to hardcore prioritize the ones that are about anything related to quality of cryopreservation. And for those slightly funny questions that some people might want to ask, we're also going to deprioritize them today. In fact, those I'm not going to answer today. We're going to do a specific section about funny questions that might not be 100% serious next time when we do the AMA and the Q&A. So those are all going to be answered next time. All right, without further ado, let's talk about what we consider the principles of quality. So for me, quality is kind of the thing that we try to think about the most. And I also do, of course, there's team members who think about communication of cryopreservation, how to grow the field and so on. But all of that is indirectly in the end related to quality. So for example, if we would have significantly more members, we would be able to have significantly more teams, which then allows us to have faster response times, less delay in last-minute cases. It would also allow us to have higher, from a cash flow perspective, put more of cash flow into research, which again then helps quality. But from a direct perspective, how we think about quality is, I think the guiding principle that we like to always keep as the highest thing is that quality is never good enough. The reason why I'm saying that is of course it's unknown when and how it will be possible to revive someone from cryostasis. We of course have an understanding. We published a paper a while ago together with a few other researchers, where we ask neuroscientists what type of neural structure, what level of detail needs to be preserved so that memories will be preserved. And of course, so we have an understanding what is necessary for the things that we care about: memory, identity, personality, consciousness, all of that. But of course, this is not a comprehensive, this is not a guarantee that this is actually the case. So I think the only approach is that we should always, until of course at some point revival is actually possible and you can prove it, an organization that works on preservation of humans should never stop saying, yeah, we're probably good enough now. So the guiding principle should always be, the mindset should always be, we're not good enough, we never will be good enough until revival, of course, and we always try to improve. What can we do to have a higher quality, a higher fidelity of cryopreservation, both from a gross structure and a fine structure on average, but also in the top 10 percentile of cases, but also in the bottom 10 percentile of cases, and so on. Metrics for that are very, very important. So how do you know if a cryopreservation case actually went well? And of course, I'm going to elaborate in that in the end, but having strong metrics is kind of is absolutely crucial and vital for being able to actually evaluate quality and then try to get better. And last but not least, we have this kind of guiding principle that whatever happens in a cryopreservation case, if someone is, let's say someone is in cryostasis, whatever happened before that, we take responsibility for everything. Right, and I'm going to elaborate a bit on that, of course, as well in the course of this event. We kind of separate in what we call indirect and direct responsibility. But we never want to say something didn't go well, yeah, but it was outside our control, right? It was outside of our responsibility. Right? This includes like extreme things, like if someone dies without us knowing, right, and we're only being notified after that person has already died. Of course, we don't have any direct responsibility for that, but we could have told that person more that they need to tell us if they have any medical conditions, right? Of course, I'm not arguing that will solve all problems, but I think this is a better principle to think about quality, so that you always try to think, if something doesn't go well, what could you have done? What could we have done as an organization to improve or not have that problem arise? So these 4 things are our general, foundational guiding principles about quality. Quality is never good enough. Never stop improving. So I kind of already talked a bit about it. Saying we're probably good enough. Right? Of course, we don't know for sure if we're good enough to, allow revival in the future, even given very, very advanced technology. But saying something like we're probably good enough, I think it's a very dangerous thought. It kind of lets you be complacent. It lets you be like, we already have our goal achieved, or at least probably. Why do we need to continue pushing? Why do we need to do everything we can to improve quality? So that's a thought that is not allowed at Tomorrow. So we never want to fall into this trap of believing we are probably good enough, we don't need to improve anymore, it's going to be fine. If in the future, people wake up and the doctors, and I kind of tell that kind of mental picture sometimes, if the doctors, or whoever is the person who revives those people from cryostasis, say, hey, the team that cryopreserved you, they did way too much. They could have stopped with that technology from 20 years ago, right? Everybody is being revived. And if that's the case, amazing, right? Then, then we over-prepared. But I think this is very much a topic where I much rather over-prepare than under-prepare. Definitely better to be safe than sorry if you think about the probability of revival in the future and how good cryopreservation should be. So our goal is to never be happy with what we have in regards to quality, always try to get better. There's probably something in the future that we will figure out how, even if you reach all quality metrics that you currently can think of, right, and you're always at 99 percentile or whatever, in the future there will probably be something where we have a deeper understanding of how neural processes, how neurons, how everything works in the brain, how we can then improve a bit more. At the very least, we can improve on average, right? It's possible that at some point we're getting pretty good with the top 10 percentile of cases, but then you can improve on the average, right? You can extend your coverage area, and so on and so on. There's always something to do, and this is kind of what we want to do. The second point or the third point is kind of this metrics point. We consider kind of 2 types of metrics. There's one, what we call core metrics, and then there are outcome metrics. Core metrics kind of form the basis that you use or collect during a case. Most of them, in fact, I think all of them, give you guidance of what you need to do during a case to improve the outcome, to improve the outcome metrics. So core metrics would be something like, you do a cryopreservation right now, someone died, you took over. Now you need to cool that person very quickly. So how fast you're able to drop temperature, right, is one of those core metrics, right? And you can see this. Our data loggers that we have, they give you a cooling rate, right? So you have an understanding of how many degrees per minute do you drop the temperature of the body? Meaning, how short is the person exposed to high temperature? And high temperatures in this case, of course, leads to ischemia, which leads to degradation, faster degradation. So, and of course, if you see, well, our cooling rates are not in line with what we expect, you can still do something about it, right? End-tidal CO2 would be another one. So end-tidal CO2 means it's a measurement of the CO2 that you breathe out. So when you do chest compressions and you have a ventilator, so giving oxygen, you can measure how well your chest compressions and how well the gas exchange in your lungs work, right? And if you don't see good values there, maybe your chest compressions don't run well, maybe your ventilator doesn't go well, maybe there's some blockage, whatever, right? At least you can do something about it. You can investigate. Then, of course, once you're done with SST, like the initial stabilization at least, then at some point you start perfusing that cryoprotective agent. Now, cryoprotective agent perfusion needs to be done in kind of, it's not super narrow, but in a narrowish pressure range. Right? You don't want to have too much pressure because that might burst blood vessels. You also don't want to have too little pressure because then the capillaries don't open and you don't get the cryoprotective agent into all parts of the brain. So it should be in a narrow range. So pressure needs to be tightly controlled and is a metric that you can then take a look at during perfusion. Then you collect on the venous side. So on one hand, you put cryoprotective agent into the body, and on the other side, right, you take the low concentrations of cryoprotective agent that have now flown through the body and have diluted with water and so on. That cryoprotective agent you take out. So you measure the concentration of that cryoprotective agent that you take out of the body with the so-called refractometer. So you measure the refractive index. So over time, initially you want to start slow, right? And then you increase the concentration of cryoprotective agent in a slow curve. You do this because otherwise you might get osmotic damage, which of course you want to absolutely avoid. But at the end, you want to have a concentration of cryoprotective agent on the venous side of the body where the cryoprotective agent comes out of the body that is high enough so that you can estimate that the perfusion is complete, that everywhere in the brain and ideally also in the body, the cryoprotective agent concentration is now high enough so that you don't have ice crystal formation when you cool down. Now, so if you look at our case reports, right, you see these curves where in the end we want to be in the target range. If, for example, during a cryopreservation case, now that curve doesn't rise fast enough and like in a non-standard way, you know that something might be wrong and you might need to figure out what you can improve. At the same time, you see some degree of dehydration, right? So cryoprotective agents take out water from the body. So you see a dehydrating effect in the arms and also in the legs and in the face and so on. So that is something that you can use as a measurement on site. And at the same time, you want to avoid swelling, right? If you have swelling in the body, especially in the brain, you need to stop, or you need to potentially stop perfusion. So you don't want any swelling. So all of these metrics are metrics that we collect live in real time during the stabilization procedures and the cryoprotection procedures on site, and then adapt if something doesn't go as it's supposed to. These are all metrics that we have direct control over, right? So if something goes wrong here, then, well, that's on us. We need to, it needs to be better equipment, better training, whatever, right? At least it's directly on us. So the difference between these core metrics, again, is core metrics you have in real time. You can still do something about them in the individual case. The other type of metrics that are very important are so-called outcome metrics. These are metrics that you collect after the whole procedure. In fact, most of them you collect when the body is already in long-term cryostasis. So if you see something didn't go well here, and if you see something in those metrics that should have been improved, there's nothing to be done anymore, right? The body is already at cryogenic temperatures. You can't reperfuse, you can't do anything about it. So in the end, on average, these are the most important ones because they show you the actual quality of cryopreservation. So this is where it matters the most, right? There's pretty much two main metrics here. One is CT scanning, right? And of course, we mentioned this multiple times, and for those of you who have been part of our case review or annual case review live events might remember there's always CT scans in those cases. So pretty much after the whole procedure is done, in our case at cryogenic temperature, so at negative 196 degrees Celsius, we CT scan the brain and the whole body to get information about how high is the cryoprotective agent concentration in the brain. And for those of you who might not, who weren't there or might not remember, I have some pictures in a second. So there should never be a cryopreservation case where there is no CT scan data published, right? Without that, everybody can claim, you know, this is a great cryopreservation, everything went super well. The CT scan is the main metric that every case should have. Except for, I think we have one case where we don't have CT scans. This is a case where we have, where it was an SST only case, so where we just did the cryopreservation, sorry, the procedures, right, and then sent the patient to another storage location that the patient had chosen. In that case, you know, if they don't do a CT scan, we unfortunately cannot do a CT scan. Even though in the future, if possible, if logistically possible, we might try to go through Switzerland to then do a CT scan and then continue from there. But of course, that's sometimes logistically not possible, and should also not be done if there is a quicker flight. You know, if, for example, if there is only a flight in a couple of days, or the documents still need to be completed or whatever, and we have time, we can do that. Otherwise, that's not advisable. So, but otherwise, every case should have published CT scans. Now, CT scans tell you if the cryoprotective agent has gotten into every part of the brain, right? In the end, it tells you if there's enough cryoprotective agent that ice crystals cannot form in these regions, or at least the ice crystal formation is reduced significantly. So it does not tell you, necessarily at least, how good the fine structure of the brain is. It's more so that if you have a bad CT scan, you pretty much don't need to look at the fine structure, it's going to be bad. But if you have a very good CT scan, you still need to look at the fine structure. The fine structure of the brain, the so-called ultrastructure, you look at by doing electron microscopy. For that, we need consent, and of course we talked about this for a few times already. We need to consent from the person who decided to be cryopreserved that we are allowed to take a microsample, in fact 2 or 3 microsamples, very small samples, from their brain and or their spinal column. So you can say, hey, you can take 2 small samples from my brain, that's okay. You can also say, well, brain I'd rather not do, but spinal column is fine. In the end, these samples are the same type of and the same size of sample that you would also take during neurosurgery. So based on our current understanding, this is probably not a big effect, but of course it's up to everybody to decide if they want to allow that or not. We have now one person who has given consent and who was then cryopreserved in the past, and we're still in the process of analyzing the electron microscopy. I'm going to show you 2 pictures, but they're not fully analyzed yet in a second. And then down the line, of course, we're gonna publish those as well. In the future, those ultrastructural preservation data, again, if we have consent, should then always be part of the case reports, right? Because in the end, that is what kind of then after the CT scan tells you a lot about how the cryopreservation went. If you don't have EM data, electron microscopy data, meaning, for example, if the person hasn't given consent, you can estimate the degree of degradation effects to the brain based on temperature data, so-called SMICs, standardized measurement of ischemic exposure, meaning it gives you some understanding of how much, you know, fine structure damage and fine structure degradation there was. Nevertheless, this is definitely significantly worse and has a lot of caveats compared to electron microscopy. So these 2 things are absolutely vital. CT scanning and then whenever there's consent, also electron microscopy. There's a couple of pitfalls for these types of quality metrics. So if you compare, you need to be aware. The most important one is that for temperature at least, is that since we are measuring temperature, or we want to measure temperature in the core of the body, right? So normally there is a rectal temperature probe, and then in our case there's tympanic temperature probes. Some people also put temperature probes into the nose. We use the nasopharyngeal space for cooling, to have faster cooling rates, so we cannot use the nose. The problem in general is that even if you use the nose or tympanic, doesn't matter, since you have ice water flowing around the patient, potentially above the ears, right, and so on, in our case always above the ear line, to be able to cool faster, these temperature probes can get in contact with ice water. So if you have very, very fast cooling rates, very low ischemia times, if expressed in SMICs, those are not relevant or not realistic, right? So with current technology, if someone says, we've been cooling the patient, between 0.5 and 1 degree per minute, that's not possible with current technology. That means then the temperature probe was somehow exposed to ice water. So it needs to be a realistic temperature curve, right? If we see this in our cases, you will see either the data is there and we say, hey, the graph is not there, and it says there was no meaningful data, could not be collected, or the graph is there, and then on top of the report it says that this data should not be considered correct, and there might be significant mistakes. That is one of those. Exposure of the thermocouple, the temperature probe, to ice water is a very, very common mistake and problem. Which also then leads to the SMICs that I already briefly mentioned. If the temperature data is not correct, the SMICs calculation is not correct, so it's not meaningful. The SMICs also it's not necessarily a pitfall, but kind of more a note. It doesn't tell you anything about how well perfusion went. SMICs only tells you how good the cooling rate was. It indirectly tells you a bit about perfusion, of course, because perfusion cools down, but it doesn't tell you that, for example, the whole brain is well perfused. So also a bit of a, it's a surrogate. EM data is always better. SMICs is just, it's a surrogate. It's something that at least you can do something if you don't have EM data. For CT scanning, very important that it's being done at a stable temperature, right? We do CT scans always at cryogenic temperatures. So in our case, if it's an ITS doer, it's going to be at negative 140 degrees about. If it's an immersion doer, then it's at negative 196 degrees. So we literally scan people in liquid nitrogen, because of course we don't want them to warm up. This is absolutely not acceptable. So the person with fully immersed in liquid nitrogen goes through the CT scanner to be able to do this at a clean, stable temperature without the risk of potentially warming up. And last but not least, we have this always published, how we do calibration. Calibration of those CT scans need to be done well, because of course you need to relate the density data. That's what a CT scan tells you. It tells you the density of different parts of the brain and the body. Those you need to relate to the concentration of the cryoprotective agent. Now, to kind of show you these, and of course most of you probably have seen them already, this is one of our CT scans from one case where I had the picture. I think it's from 2024, if I'm not mistaken. That is a CT scan how it's supposed to look, right? Of course, these CT scans are always in pseudocolor. This pseudocolor tells you what is the concentration of that cryoprotective agent here in different parts of the brain. Long story short, the scale goes from green, high enough concentrations, through yellow, there is cryoprotective agent but not sufficient concentrations, to orange and then dark red, and then in the end to blue. Blue means ice. Red means there is some cryoprotective agent, but definitely not enough. Orange, cryoprotective agent concentrations rises. Yellow, there is good amount of cryoprotective agent, but not enough how much we want. And then green colors mean there is enough cryoprotective agent to not have ice crystal formed. Here in this case, you always see some yellow inside the brain, but it is, in this case, for example, completely in the ventricles and in the dural sinus areas where there is no brain tissue. So those areas don't need high enough cryoprotective agent concentration. The rest of the brain, and this is the quantification for it, it's always like close to 99%. There's two lines that we always give. You see a dark green, I hope you see this on the screen, but there's a dark green line and a light green line. These are the lines that correlate to 100% of target, which is 65% weight per volume. And then the light green line is 92% of target, meaning 60% weight per volume. The reason why we're doing this is the range where above it no ice crystals can form, and now it's not 100% clear. Likely 60% in tissue is sufficient, but just to be sure, we want to give both lines. 65 is definitely sufficient, 60 is likely sufficient. And then these other lines that I mentioned, you see the red line, you see an orange line, you see a green line, sorry, a yellow line. These are far away from the density values that we see. So, this histogram that you see, these are the density values of the CT scan of one slice, of course. But then, since we always publish multiple CT scans, you can look through the brain, right? Which is also, by the way, a very important point. One slice, if CT scans basically show you slices, right? You see here basically 3 slices through different kind of, different planes, but they only show you one thing. So basically only one snapshot, right, in one plane. In our case reports, you always see multiple slices, right, so that you can see that there is not an area where whatever we just picked the best looking areas, and we always have the same cuts about the same areas where these slices are being taken from, so that you can compare CT scans between them. All right, so this is CT scanning, as I said, most important. And last but not least, in those CT scans, you also can evaluate the amount of shrinkage. So here you see one of those analyses. We always give this in percentage. How much has the brain shrunken? Currently, brains that are perfused with cryoprotective agents do shrink. The reason for that is that these cryoprotective agents dehydrate the brain. They have a high osmolality. They dehydrate the brain. Mostly because the blood-brain barrier is intact. So there's an area, like a covering around the vessels of the brain that doesn't let the cryoprotective agent easily through, but can draw out water. So currently some amount of dehydration, even large amounts of dehydrations, are in fact a metric for good quality. Not necessarily for good quality of ultrastructure, of course, because the brain is shrunken, but it means that there was low amounts of ischemia, that there was no waiting period before the team was able to start. In the future, of course, this should not be the case anymore once we implement so-called blood-brain barrier modifiers. Basically, these are chemicals that open the blood-brain barrier to the right amount. At that point, we would then not have that shrinkage effect anymore. Of course, once that is the case, we're always going to note in the case reports that was the case with blood-brain barrier modifiers, or for whatever reason, if there is any reason, without, so that people understand if shrinkage should be observed or not. This is ultrastructure now, again, like very early, like preliminary images. There will be a comprehensive report, of course, on those. This is from the first person where now we were able to take ultrastructure samples, just to give you kind of a visual impression. So these are all the cells in the brain and the synapses and so on. And now, of course, we're gonna publish this once we have all the data and fully analyzed. Very likely, CT scanning, there isn't much to do anymore. When we go back here, this is like 99-98%. So very, very close to where you can be. On ultrastructure, there will be probably years and years of optimization until this actually gets good. At least when I say it gets good, in an average case. it's still possible that under, you know, kind of lab-like conditions, or like with very low amount of you know, with perfect external conditions, you would be able to get very good ultrastructure preservation already now. But of course, our goal is always to be good on average, right? And even then, you know, a large range of the percentiles to have, so that almost everybody, or hopefully fingers crossed, everybody gets a good preservation. So there will be much more talk about this and much more information about this coming up. Now, last but not least, this kind of concept of we take responsibility for everything. As I mentioned briefly in the beginning, we separate into what we call direct responsibility or indirect responsibility. Pretty much direct responsibilities are things that we have direct control over. If something isn't good there, we fucked up. Like there was a clear fuck up on our side. So this is if we make mistakes, you know, whatever the mistake might be. You know, we didn't take something, like we did a procedure wrong, we didn't inform the patient of something, like something where we should have done better. And of course, it's always important to remind people, cryopreservations, human cryopreservations are they more like emergency medicine than there are like procedures under lab conditions. So stuff is going to go wrong, right? Like it's not something where you can just, you know, if you're not ready, you just repeat the experiment tomorrow under lab conditions, right? And of course, in the labs, you optimize for a long time, and if something doesn't go right, you do it again, and then you do it again, and do it again, and at some point it works. Cryopreservation is, you know, someone has just died. You need to do everything now. The team needs to be there now, and so on and so on. So it's a different environment. So from that point of view, stuff is going to go wrong. My point is always, I want to do everything to reduce the amount of stuff that goes wrong. And then if you look over longer periods of time, the quality of an organization needs to go up, right? If it stays the same, then, like, you know, what are we doing? Like, you know, so the trajectory needs to be right. And, you know, if you remember at the end of our case reports, we always have a list of things that didn't go right. The point here is not necessarily that stuff cannot go wrong, because it will. It's more so that stuff, you know, when we reported like these things went wrong last year in the case reports, then these things should not all be the same this year, right? And then there's a problem that is a bigger problem. And so new problems might come up, but the amount of problems and the severity of problems should go down, and problems should not repeat themselves. So it's these types of things, you know, where if our teams are not well trained, right? If our equipment wasn't right, if we forgot something, if procedures weren't the correct ones, and so on. So this is direct responsibility. Now, the rest is basically everything that's not direct responsibility is then indirect responsibility. Indirect responsibilities are things where we did not have direct control over it. The best example here, again, being that I already mentioned, is if someone calls me now, right, and says, hey, I just found the membership card of one of your members. That person has just, has died yesterday. And then, of course, I would leave this live event and we would start running and try to get to that person as quick as possible. So, of course, since we've been just notified, right, after that person had already died, there's not much that we directly could have done. But indirectly, we could have done something. So we could have, for example, told that person, let's assume that person died due to some disease that they were already aware of for a couple of weeks, right? But they thought it's not that bad and probably everything's going to go well. Now, we could have told our members more aggressively, more often, right, that they should tell us if something, even if it's not something big. Right? If someone calls me now and says, hey, I just found this membership card and, one of my next of kin has died yesterday and they were a member with you. We could have told our member, hey, if you die, you need to tell your family that they need to call us immediately, right? Not a day after, right? So we could have done something. And so the reason why we do it like that, we don't want to build an organization that just, says, hey, yeah, listen, we could have not done anything. There's usually something that you could have done. It might not have a tremendously big effect, But if something goes wrong, I think it's prudent to think about, okay, so what are all the things that we could have done? Similarly, there are some countries in the world where cryopreservation is more difficult than other countries. There might be countries in the future where cryopreservation is, due to new laws, is made really difficult, if not impossible. Right? In this case, of course, I would argue we would have an obligation from an indirect responsibility perspective to tell people, hey, if you're not doing that well, if you're being diagnosed with a terminal condition, you need to go to another country, right? Your country currently does not work well, and so on and so on. So all of that stuff is indirect responsibility, including stuff like making sure that if people get, if they need cryopreservation, that funding is in place. The list is very, very long. It's everything where we don't have direct control over. And yeah, last but not least, that's kind of the guiding principle for this point. So to kind of separate and kind of give a bit of an understanding about these like indirect and direct responsibilities, right? If you look at our case reports, you're going to see these tags. We don't have them last year, but we implemented them this year, right? So for example, one is a tag that says post-death notification. This means like, we were only made aware that this person died we were made aware after that person had already died, right? Again, indirect responsibility. Then there can be last-minute cases. Last-minute cases would mean, we're being told, someone wants to sign up now, they're going to probably die in the next, I'm going to probably die in the next, week, can I still sign up, right? Still indirect responsibility, right? Even though for that very specific person, it's very difficult to maybe have done something, but we could have had a clearer public communication that says, hey, if you consider cryopreservation, tell us as early as possible. Don't let it wait until, it's a last minute case, right? Then there's non-members and members. Have they signed up with us before, or do they need to do the whole sign-up process? Then there's payment not clear and payment in prepaid. Of course, in most cases, people who sign up for cryopreservation, they put payment in place. But then again, there's also people who say, listen, yeah, I'll take care of that later, and all my family is going to pay, or like these kind of like highly not advisable things, right? Then there's whole body and brain only, and then there's SST only. SST only means someone is signed up with a storage organization somewhere else, and they, for whatever reason, die in Germany, or they feel like we do better SST work, but for a variety of reasons they might want to be stored somewhere else. Then people can also just sign up for us with SST. And last but not least, they are what we call partner cases, where we have decided that we partner with a local organization for more comprehensive SST coverage and perfusion coverage. And of course, in our last event, right, when we talked about the case reports, we talked about some cases that were handled by RBS in the US, where we were not that happy about the quality. But again, it's still our responsibility, right? Like, we have decided that we're gonna work with that organization. And now, over the last weeks and months, we've been actively working on improving quality in the US, and we will continue to do so, right? And hopefully, fingers crossed, I might have some good news to share relatively soon on that. But it is also our responsibility, so also indirect responsibility. All right, since I'm pretty sure this question will come up later, why don't we just do ASC, all this ultrastructure stuff and, and fixation and so on, right? Of course, there is kind of sometimes this discussion, like, under which conditions should you do cryopreservation, under which conditions should you do aldehyde stabilized cryopreservation or fixation, so chemical fixation, and so on. So I thought, if you talk about quality, there should be a slide on that. So first of all, we're very open to these approaches and these types of preservation. In fact, as we have said many times, and as we also have some case reports every year, if there are high ischemic cases, right, we already do immersion vitrification. For some brain cases, we do immersion vitrification as our standard procedure. So by no means am I against this, right? Just from a field perspective, it's always, I kind of already mentioned that, it's always important to remember there's lab conditions and there's real world kind of emergency medicine-like conditions. ASC has good data, even though, of course, most of you might know, 21st Century Medicine published now data on their brain, their ultrastructure after cryopreservation as well. So most of the data, if not all of the data, from aldehyde-stabilized cryopreservation, it has not been done in field settings, right, with low ischemia. They have not been done with teams that are remotely and handle those cases and handle them potentially far away from their facility and so on and so on. So it is not a comparison that makes a lot of sense. You cannot compare lab conditions or lab-like conditions to emergency medicine conditions, right? If down the line, right, there's organizations that have demonstrated that can be done and can be done well. Again, we're super not against it. We might even be one organization that would try to evaluate this, right, and see if this can be done, right? Not necessarily to rely on others to show this first and then we're doing it as well, but also actively get involved in this. But as it stands right now, this has not been demonstrated that this is done in the field under low ischemic conditions in humans, right? There's animal data, there's data from medium to high ischemic conditions in localized areas and so on. So there's some stuff, but it's not really under real world conditions. So I think that needs to be done. Plus, there is a tremendous amount of disagreement and differences in opinion in the field that argues for fixation, mostly about how fast that procedure needs to be done after circulatory rest. Cryoprotective agent perfusion is more forgiving. I'm not saying you should do this late, but you can do this later. At least that's the argument where some people argue that aldehyde-stabilized cryopreservation needs to be done quickly, extremely quickly after circulatory rest, within minutes, right? Which, of course, from a logistic standpoint, makes it very, very complex. And last but not least, if you want to be good at a complex procedure, you can unfortunately not do everything. We're still improving our procedures, our teams, and we will for a long time. If we now would add on aldehyde-stabilized cryopreservation or chemical fixation as one of the options that people can choose, then we run the risk of not being good at anything, right? Because then it's not like there is we have done all the training and we're now perfect with one and there's nothing to improve anymore, and now we can add on new complex procedures. So I'm a very strong proponent of relatively strict prioritization. So for now, our priority is to get cryopreservation really, really good. Once we are really, 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 really good, then we have the capabilities, right, and also we have a larger team and more funding and whatever and more members, then we can add on more things, but it cannot be done too early. Too early means later on you would not be good at cryopreservation anymore and you would not be good at aldehyde-stabilized cryopreservation and fixation. And since there are organizations that under certain conditions at least offer ASC and fixation, there is an option. Again, I think there's a lot of logistical challenges, but at least it doesn't seem like, if we don't do it, no one will. So for the time being, we're going to focus on cryopreservation because of these reasons. Mostly because it hasn't been demonstrated yet under real world conditions. And last but not least, because of the logistical challenges of being good at two things. All right, coming back as a reminder to these principles. So this is what guides quality at Tomorrow Bio. Quality is never good enough. We should never think it's probably fine, we don't need to get better. At every day of the week, every year, we need to say, what can we do to improve quality even further? Metrics is kind of the underlying and most important, it's the basis, the metrics form the basis of kind of that approach, right? Both these core metrics to kind of measure in real time, during procedures, how to improve if something doesn't go well, and the outcome metrics, CT scanning and electron microscopy. I wrote an article, these are the 9 questions about, what should you do, what should you ask an organization, a preservation organization, if you want to sign up with them. And one was, if there's no case reports, really big red flag. If there are no CT scans published, also red flag. So there is no good reason why organizations shouldn't publish CT scans or do CT scans. Metrics very important, and last but not least, we take responsibility for everything. And there, this comparison, or this difference between direct responsibility and indirect responsibility. All right, and now I would like to briefly mention another event again. Scan this QR code. If I'm not mistaken, it's on April 27th. But scan the QR code. I might be wrong here. That's a Q&A and AMA, so you can ask any questions you want. It's going to be with me and Fernando. From, strategic choices, you can of course also ask about quality, but anything and everything you want, and we're going to reserve 10 to 15 minutes to answer all your slightly funny, maybe not 100% serious questions. Today, those questions will not be answered. In fact, my team will probably get rid of them so that I don't get tripped up by them. But next, that's not next week, but in our next event, those are welcome as well, at least during a certain time frame. Today, again, we're focusing on quality questions. Now, this is the second QR code. This is again the QR code for Slido, which is this Q&A tool. And now I'm gonna start going through these questions. All right, I'm going from the top again. If there's anything that you want to upvote, downvote actually doesn't work, but you can upvote questions that you deem interesting, and then I'm gonna prioritize them. Do you have any research planned for supercooling, which does not require vitrification solutions in order to prevent ice crystallization? If you mean by supercooling extremely quick cooling, so quick that you in fact do not need cryoprotective agent, then no, we don't have any plans there currently. The reason being, these types of cooling rates in sizes like a human body, I'm not aware of currently of any way of how this might be possible, right? So there are some techniques like persuflation and so on that might allow you to have less cryoprotective agent concentration, right? Which would be an advantage, would be less toxic and so on. But no cryoprotective agent would not be. I don't see a reason how this would be possible, or like no way how this would be possible right now. You monitor physical parameters pre-cryopreservation, but since EM is only assessed after storage, how do you account for baseline tissue quality? So for electron microscopy images, there are electron microscopy images in literature that show you, so this is how it's supposed to look like. This is how the brain is supposed to look like. So you can compare against them. Of course, during the cryoprotective agent perfusion and then also the preparation of samples after cryoprotective agent, there's changes to the tissue. There's potentially even like preparation artifacts. You need to unload cryoprotective agent, for example. This is the first time we've done that in this sample. We already found a range of things that we didn't do perfectly well. So there's already improvements that we're gonna make. So some of the how that brain or these samples look, or these ultrastructure images look, might be due to how we prepared them, how the procedure of preparation was done, mostly the unloading. So there will be improvements, but once you have done all of that, you can compare to existing images of how that structure is supposed to look like. Based on the US case reports for 2025, the results were not that good. What has been done so far to improve that? So indeed, we were not super content with the quality of those case reports, right? And not only not those case reports, there can always be circumstances, but also not the reason why the quality in the end was not that good. So what we've done, we've gotten significantly more involved with how cryopreservations are being done in the US. The organization that we partner with, RBS, they are made up of the people who have been doing cryopreservations for many, many years for all other organizations in the US. So initially, we hoped that this all works, and we of course were involved, and we kind of gave our protocols and said, hey, this is how we're supposed to do it, and so on. Now we're close to day-to-day involved. Of course, not fully day-to-day, but really actively. So basically, my point is that we have now implemented in the US a range of training methodologies, procedures, and so on that here have proven in Europe to lead to good results. I can't say for sure yet that it will work in an outcome perspective. I'm significantly more optimistic than I might have been like a few months ago. But in the end, outcomes matter. So hopefully, again, soon I will be able to show some outcome data in the US that hopefully will already then show a significant improvement. Stay tuned for that. But long story short, yeah, we're responsible for that. So if there is no improvement, we need to build other structures or collaborate in other structures and so on, which to be fair is already partially in parallel where we're doing a bit. But yeah, I'm optimistic that in the US we will be on par with the quality in Europe very soon. What is your opinion on the balance of public publishing of CT scans and patient privacy? My opinion is that personally identifiable information does not need to be published. I don't think there's any reason. And if you go through our case reports, I don't think there's like literally nothing, I think, in personally identifiable information. But CT scans, of course, are not. Having a CT scan done, there's nothing identifiable. You would not know what that name of that person is or something like that. So I would strongly argue that patient or personal privacy has no bearing on publishing CT scans or not, right? Not at all. And if in some jurisdiction, for whatever reason, I don't know, I'm not aware of every country in the world, of course. If this is somewhere necessary to get consent, in most cases it is not, because most data privacy laws don't even apply to people who are diseased, right? And based on legal systems, of course, currently people in cryostasis are dead, right? So mostly it doesn't even apply in principle, but even if there is a country where it might apply, then it would be in the responsibility of the organization to get consent before people get cryopreserved. All right, are you gonna collaborate with Cryonics startups, e.g. Until Labs, for improving cryopreservation techniques? So we're generally super open to collaborate with everybody, anybody, right? So we collaborate with multiple private labs, with other startups, with universities, with hospitals, and so on. So from our side, we're always open. Of course, there needs to be a meaningful collaboration, right? Something that actually makes sense. So if that's the case, we're always happy to collaborate with everybody. What are your thoughts on preservation with versus without aldehydes? Is there consensus? Are there pros and cons? So without aldehydes, it would mean it would be vitrification based cryopreservation, and then with aldehydes would be like aldehyde stabilized cryopreservation, for example, or just fixation. So I briefly, maybe this question was asked before I had my slide about this topic, and so if not, then feel free to elaborate and ask follow-up questions if I'm now cutting it too short, if there's a specific question. So yeah, we're open to it. I think it's interesting technology. There's definitely no consensus on how important it is and so on. It's very difficult to deliver in remote settings and so on. So there's logistical complexities. So for the time being, we're focusing on vitrification-based cryopreservation, except for these cases where we already anyway do immersion vitrification, which is aldehyde stabilized cryopreservation, but via immersion. How do chances of future revival change when there's a delay between death and preservation start? If you had to put a number on it. So unfortunately, I definitely can't put a number on it, but directionally, so the problem is that the opinions go so far, they differ so far, right? There's good scientists that say like it's minutes, right? There's also, I think, good scientists who say, or based on, I think they're good scientists, like, they say, like, hours and like many hours even. I really don't know. So the reason why I say I really don't know is because it's so difficult to predict what future technology will be able to do. Like, we're living through one of these kind of paradigm shifts right now. 10 years ago, LLMs like, Claude, OpenAI, Gemini, and so on, this stuff is not imaginable, right? And I always use, of course, the example, like 50 years ago, iPhones are not imaginable. It's not like we kind of got a, we have a concept of it, and then, no, iPhones are fundamentally not imaginable just, 50 years ago. So I have, so I have a very hard time making any strict predictions here, but directionally I can say cryopreservation should be done with the least possible delay, but it should always be done if the person decides that they want to do it, right? So if it was the person's wish, right, and they made that wish or that declaration, that decision for themselves before death, right, then it should always be done. The reason for that is it's morally better if someone in the future who wanted to be revived cannot be revived because they were cryopreserved too late. It's morally better that that happens than if someone who wanted to be revived and then we said, hey, it's too late. Like we put an arbitrary line somewhere where we said we only do it in a certain amount of time after death. And then it turns out that in the future that person could have been revived. Since we rather want to be wrong this way around, so we rather want to cryopreserve someone who wanted that, of course, who then it turns out cannot be revived. Our guiding principle here is we always cryopreserve you, given you have made the choice, and we always try everything to do it as quick as possible and under the best possible conditions. What are the main developments in this period? Can we be optimistic? We can definitely be optimistic, but we should definitely also not be, delusional and think cryopreservation is a tremendously big field and so on. So we definitely need to get bigger as a field. We need to work on it. Much needs to be improved, right? So, that's my point. I don't ever want to be optimistic in regards to that I think now we're good enough. I want to be optimistic in regards to that I think it's worthwhile to push forward and try to make it work and not give up, but then use that motivation to always get better and not get complacent. Right. Right. What are implications for you of the recent paper about preservation of ultrastructure with aldehyde fixation, even when preservation was delayed? I think, first of all, tell me which exact paper. There were a couple recently about preservation of preservation with okay, now the question is gone. With aldehydes. I think this would go beyond the. I don't think there is any specific impact, or at least nothing comes top to mind. I don't think there is any specific impact to the things that I said today. I'll think about it. If I come up with something, we can follow up on that question next time. How far are you in development of new CPAs? Do you plan to optimize the CPA to improve overcoming the blood-brain barrier? So fundamentally, new CPAs I think are not super close. Luckily, there's a couple now new organizations that I'm aware of that are starting to kind of take that approach to trying to make new CPAs, right? Some of which we're also supporting. So hopefully there will be more significant development coming up. Blood-brain barrier modification is in fact something that we're currently actively working on, have a lab work on. So I think the next bigger change for us will be, there's always smaller changes. So we recently, for example, changed the ramp curve of our CPA. So that will be implemented in our next case. So smaller changes are constantly happening, but the next bigger one will be blood-brain barrier modifiers. So those will be small amounts of SDS in the cryoprotective agent and in the washout solution, in the cryoprotective agent that then opens the blood-brain barrier. So that will be something coming up soon. What is progress of your development of cryogenic air transport? It's extremely difficult. So currently, when you transport by plane, you cool the person with dry ice. Right? In an ideal world, you would like to transport them lower than negative 140 degrees Celsius. So at cryogenic temperatures. The problem is you are not allowed to take liquid nitrogen on planes, because liquid nitrogen makes nitrogen. 1 liter of liquid nitrogen makes 700 liters of gas form nitrogen, which might, of course, suffocate everybody in the plane, so that is not allowed. So there are some techniques how you can transport at these temperatures. Small volumes work, large volumes are very difficult. A while ago, we did like some exploratory research project of building like a chamber that allows you to cool to cryogenic temperatures and then transport on cryogenic temperatures without liquid nitrogen. The project was not super successful, so it would have taken significantly more investment and time to put it into, and we just deprioritized it. It's not the most important thing, especially since the cryoprotective agent we use is highly stable at dry ice temperatures, and if you increase the concentration slightly, if you expect long dry ice shipping or longer dry ice shipping, then you avoid the ice crystallization in that or the ice crystal growth during that transport time. Plus, initially, when we were not that experienced with long air transport on dry ice, we thought this might take significantly longer. It can be done pretty quick. So from a priority standpoint, again, we're very strongly on hardcore prioritization, given that the field is pretty small and there's a lot of things that can be improved. Currently, this is not a priority. Are there areas of the body, other than the brain, where it is difficult to perfuse correctly? Yes, in fact, the brain is relatively easy to perfuse. Also, of course, given that we focus on the brain and have the most experience with it and so on, there's other parts of the brain other parts of the body that are very difficult to perfuse. So, for example, the lungs are very, very difficult to perfuse. And some of you might have seen this. I think we're actually the first organization ever to do that. We have done whole body CT scans at cryogenic temperatures. So we see how the whole body, how well it is perfused. The lungs are usually not well perfused. Luckily, of course, the lungs, currently you can do lung transplantation, right? In the future, it's very likely that lung transplantations, fingers crossed, will be easy. Plus, you might have 3D printed lungs and so on and so on. So it's not probably the worst, but down the line, we would optimize. But the first optimization is still on the brain on electron microscopy. Also, the gut is difficult to perfuse. So there's a range of different organs that are not easy to perfuse. The brain, luckily, again, because also, of course, we focus on it, is comparatively easier. Are you currently using microphones to monitor the formation of brain fractures during cooling? No, we do not. We might implement that at some point, but we do CT scanning after cool down, right, at cryogenic temperatures of the whole body. So if there's at least larger fractures we see in the CT scans, microfractures that I'm not sure if there are microfractures that you might see in the microphone, but you would not be able to see them in the CT scan. Possible that this is the case, that we would need to evaluate at some point. But for the time being, we are focused on the CT scanning. Where will the containers going to be placed? How will you ensure safety from environmental influence for years, decades, centuries? Okay, very quick answer. The cryostasis is, our cryopreservation location is in Switzerland, underground. As much as possible, or as much as one would know right now, this is a very stable and safe location. I don't think there's something that you can much improve there. Again, these types of questions, more than happy to answer them during the AMA next time. All right, going back to the questions on top, we got this one. Is cryopreservation meaningful when the death occurs by brain metastasis? Yeah, I would say so. It depends a bit, of course, on what type of metastasis, but I don't think there's any reason, like, as long as you can get the body and the brain is pretty intact, right? Like, who knows? Maybe this is super curable in the future, right? And the metastasis, the tissue is not actually gone. It's like a metastasis, and of course the rest of the brain might be compressed a bit, but usually these don't grow that fast, so there might not actually be that much damage. But of course, this is highly speculative. I'm just saying I have a very hard time ever saying, except for, you get lost over the Atlantic in a plane and then you're being found like 4 weeks later. Okay, at some point, this probably doesn't make that much sense, nor would we probably get your body if it's in the Atlantic. But I think at least it's very hard for me to say this is a hard line, it doesn't make sense. Because again, it mostly comes from the belief that it's better that in the future it turns out that it didn't work. Then I'm saying now it doesn't work, then someone decides against it, and then in the future it turns out that it would have worked. What about isochoric freezing, a preservation technique that keeps food fresh by storing in a sealed, liquid-filled chamber without solid ice formation? I don't think there's much research. So isochoric freezing or isochoric cryopreservation means like you do it under isochoric. So it's usually under pressure, and you can't ice crystals cannot grow. They cannot really form. I don't know if this has ever been tested in larger volumes. Of course, there is research on it. I know that one of our research partners has bought like a high pressure vessel once to test this. So there might be research in the future in it. Currently for us, again, unfortunately, it's always priority list. It's an interesting topic. I would love to spend some time on it, right? We would love to spend some resources and money on all of these topics. But we need to, unfortunately, prioritize what we know is important, and these things, unfortunately, then fall down for a bit. Does your facility have bulletproof glass like Alcoa's? No, but our facility is underground, so it doesn't have any glass areas that are exposed to the outside or where someone can go. In fact, it has thick concrete walls, which are probably more bulletproof. And then again, the amount of people with guns running around in shootings in Switzerland is not. People have guns in Switzerland, but they don't run around with them. So the amount of shooting is not really an issue there. Do you think fixation is viably reversible and has comparable potential for biological revival that permits continuity of consciousness to vitrification? At least I don't think there's any strong reason. So this is kind of like, we're comparing like far away things with unclear probabilities and so on. I don't think there is. I think it's comparable probably, like it's napkin math, right? It's napkin math or napkin concepts or napkin physics. How I would imagine that relatively advanced nanotechnology in the future works. I don't think there's any fundamental reason why this should somehow not work for normal biological revival, right? There's nanotechnology experts who could give a significantly better answer here. It might be something that is more difficult, but I don't think it's like orders of magnitude more difficult or something like that. So I think this is not. I think this is so. In the past, the people who advocated more for fixation, aldehyde stabilized cryopreservation, this was somehow, from a communication standpoint, always correlated or combined with uploading and whatever, right? And the people with vitrification side were always more biological revival and so on. But I think these things they mix and match, right? So this is not necessarily that you sign up for uploading if you go for fixation. So long story short, no, I don't think this is significantly more difficult. It might be more difficult, but it's not going to be like a whole different ball game. Is there a single technical problem that, if solved, would drastically reduce cost and make cryopreservation more accessible price-wise? No, probably not. The problem of cryopreservation right now, it's a combination, right? So if liquid nitrogen would be way cheaper, that would be probably the biggest impact. Probably. That would be the biggest impact if liquid nitrogen would be extremely expensive. So once we have fusion reactors, and fingers crossed, everywhere energy is basically for free, which would make liquid nitrogen extremely cheap. At that point, that might be the technology. Everything else makes cryopreservation much, much better. For example, better cryoprotective agent, faster cooling rates, and so on. Non-toxic cryoprotective agent, but it doesn't make it cheaper. I think cheaper would only be liquid nitrogen cost goes down tremendously, because then you don't need doers, you don't need complex facilities, right? You can just, you don't need to, you can just, have way extra, so you need less oversight and so on. So that, I think, would be the biggest thing. I heard the brain shrinks in cryonics preservation. Everyone that this has happened to, are they doomed, or is there a way to reverse the damage? So brain shrinkage is not necessarily clear that this is damage, right? So the idea, of course, is, and partially this has been shown, that you shrink it and then you hydrate it again, right? And of course it doesn't shrink like this, right? It shrinks, in our case, around 30% or so. So it shrinks, and then you rehydrate it, and then it basically is isomorphic, so it basically just goes back to where it was, right? There might need to be some repair, but it's not at all obvious to me, nor do I think this is the case, that this type of shrinkage somehow is information destroying damage. I think this is also something that, given sufficiently, similar to the last question, given sufficiently advanced technology can probably be fixed. Okay, that's not okay. There was said straight freeze, but that wasn't a question. If there was supposed to be a question, feel free to send it again. We know that the body starts to break down the moment we die. What is the percentage of damage to the brain that occurs minute by minute? No one knows. So of course we do know that you can revive people at room temperature for a couple of minutes, 10 minutes, 5 minutes, 8 minutes, and so on, right? With normal, chest compressions and relatively low tech interventions. So initially it can't be, at least it's not that much. There's degradation processes start, but they're not irreversible yet. We know that with cooling, you can revive people an hour after circulatory rest, potentially even longer. So with cooling, we know that for at least an hour, nothing fundamentally bad happens. Of course, we cool way more, but in percentage, minute by minute, we don't know. And then, of course, it's always very important to state, even if there is damage, as long as it's repairable in the future, it's not a detrimental problem. The damage that we don't want is that we would currently consider information destroying, where literally the part that makes you, the memories, the identity, that part is literally destroyed. And that, based on who you ask, takes significantly longer, You said supercooling is not viable currently for a whole body, but what about the brain? Sorry, I didn't elaborate. Brains are also already much too big. So the cutoff of size is not between the brain and the human, it's way before. How do the CT scans of the body compare to the brain? Is CNV, which is the concentration needed to vitrify, achieved in most parts? It's heterogeneous. So the brain, again, we focus on it, and the perfusion, of course, is fully targeted at the brain and so on. So the rest of the body is less well perfused. The reason is mostly, so we've only, a year ago or so started doing these whole body scans, so we don't have that much information yet. We have developed new cannulation techniques or additional cannulation techniques that will probably help a lot, but we haven't had the chance yet to try them out. So in one of our next cases we will, and then I can tell you more. Right now, the brain is better perfused than the rest of the body. All right, straight freeze, question mark. I assume the question is, how about the quality of straight freezes? Straight freezes should definitely be avoided whenever they can be avoided, right? But there is some data that straight freezes, might not be as bad as people in the past thought. Plus, in Robert Freyes' book, Cryostasis Revival, there is a chapter about how damage from straight freeze might be repairable. So how exactly these things compare in percentages or probabilities is impossible to say. We know that whenever we can, we avoid straight freezes to not have any unnecessary damage in the future. How does the cost of SST compare to storage cost? It's about 40% SST and perfusion, 60% long-term storage. All right, since now we're out of questions, I would like to thank everybody for joining us today. Would like to again invite everybody to joining us for our next live event, which will be this very comprehensive talk about everything, ask any type of questions you ever wanted to ask about us. Live event on the 27th of April. And until then, have a great time. And if you haven't signed up with us, feel free to reach out and talk to us and see if cryopreservation is something that you would like to do. All right.